Imagine a force so powerful that not even light can escape it, a mysterious region in space that bends the very fabric of reality. This is the nature of black holes, cosmic phenomena that have captivated scientists and the public alike. But what if these gravitational giants aren't confined to the distant reaches of space? What if, against all odds, a black hole could actually exist right here on Earth? The mere suggestion is enough to send chills down your spine, raising questions about our very survival, the stability of our planet, and the frontiers of science. For centuries, black holes were mere theoretical constructs, ideas born from equations rather than direct observation. It wasn't until recently that scientists could visually confirm the existence of these objects, making black holes one of the most tantalizing mysteries of our time. Yet the thought of a black hole existing within Earth's boundaries seems to stretch the imagination to its limits. Traditionally, black holes form when massive stars collapse under their own gravity, resulting in an incredibly dense point in space. So, how could something of such cosmic scale ever find a place on our planet? This script will dive deep into this question, analyzing the scientific evidence, theoretical models, and real-life mysteries that hint at the presence of a black hole on Earth. Could there be something hidden in the core of our planet, some anomaly that science has yet to detect? Or perhaps there's a link between black holes and unexplained phenomena like gravitational anomalies, magnetic disturbances, and even mysterious disappearances in places like the Bermuda Triangle. We'll explore these topics, examining theories that range from the plausible to the controversial, and uncovering the data that both support and challenge the notion of an Earth-bound black hole. But this journey isn't just about science. It's also about what this idea means for humanity. If we consider the implications of a black hole on Earth, we're faced with questions that stretch beyond physics, touching on our understanding of life, survival, and the very structure of reality. A black hole on Earth could reshape not only our planet but our place within the universe, altering everything we thought we knew. As we embark on this exploration, we'll analyze data, consult case studies, and dive into some of the most intriguing mysteries that surround our planet. This isn't just a scientific inquiry, it's a journey into the unknown, where the boundaries of fact and fiction blur, and where every discovery could lead to even more profound questions. So, let's begin. Is there truly a hidden black hole on Earth, and if so, what does it mean for the future of humanity? Buckle up, because this is one journey you won't forget. What is a black hole? To understand the possibility of a black hole on Earth, we first need a clear grasp of what a black hole actually is. At its core, a black hole is a region of space with an intense gravitational pull, so powerful that nothing, not even light, can escape it. This strength stems from the density of a black hole, where mass is compacted into an incredibly small space, creating what is known as a singularity. This singularity lies at the heart of the black hole, where gravitational forces become infinitely strong, warping space-time around it. Formation of black holes are typically formed from the remnants of massive stars that collapse under their own gravity after exhausting their nuclear fuel. This collapse generates an intense gravitational field, creating a black hole in the process. The boundary surrounding a black hole is known as the event horizon, a point of no return. Once anything, whether matter or light, crosses this boundary, it's pulled irrevocably toward the singularity at the center. There are three main types of black holes that scientists have classified: stellar, intermediate, and supermassive. Stellar black holes form from the collapse of individual stars and are the most common type, ranging from about 3 to 10 times the mass of our Sun. Intermediate black holes are larger, with masses ranging from hundreds to thousands of times that of the Sun, though their formation processes are less understood. Supermassive black holes are the giants of the black hole family, containing millions to billions of solar masses, and are believed to reside at the centers of galaxies, including our own Milky Way. How do black holes behave? Black holes have fascinated scientists because of their unique and extreme properties. The gravitational pull near a black hole becomes so intense that it warps space and time, a phenomenon known as space-time curvature. This distortion causes objects close to a black hole to experience time more slowly, an effect predicted by Einstein's theory of general relativity. Scientists often describe this effect with an analogy. If space were a stretched-out fabric, a black hole would be like a heavy object pressing down on that fabric, causing a deep dent around it. Any object that comes too close will spiral into this dent, eventually getting pulled toward the black hole's center. In addition to the gravitational pull, black holes also produce intense energy at their boundaries, especially near the event horizon. Matter that spirals into a black hole doesn't vanish immediately. Instead, it forms a glowing ring known as an accretion disk, where gases and particles heat up due to friction and emit X-rays and other forms of radiation before finally being absorbed. Observing this radiation has allowed scientists to identify black holes indirectly, as the objects themselves emit no light. Micro-black holes, a key to the Earth-bound theory. Although black holes in space are massive, there's a theoretical category known as micro-black holes or primordial black holes, which are much smaller in size. Some scientists hypothesize that these miniature black holes could have formed shortly after the Big Bang, when high-energy conditions may have compressed matter to create black holes on a smaller scale. While traditional black holes are usually formed by collapsing stars, these micro-black holes would have been produced by extreme densities and energies in the early universe. Micro-black holes could theoretically exist at any location in space, even within a planet like Earth. They would have a much weaker gravitational pull compared to stellar black holes and would be harder to detect because they emit little to no radiation. However, over time, these black holes would still have an effect on their surroundings, potentially influencing gravitational measurements or causing minor distortions that scientists could observe. Detecting black holes and evidence of their existence. Detecting a black hole is no simple task. Since they don't emit light, they're effectively invisible against the blackness of space. Instead, scientists rely on indirect methods to locate and study black holes. One of the primary methods involves observing the gravitational effects that black holes have on nearby stars and objects. For example, when scientists discovered the supermassive black hole at the center of the Milky Way, it was by tracking the rapid orbits of nearby stars being pulled by an invisible force. Another detection method involves gravitational waves. In 2015, scientists at the LIGO Observatory confirmed the existence of gravitational waves, ripples in spacetime produced when massive objects like black holes collide. This groundbreaking discovery opened new avenues for studying black holes, including detecting potential black hole mergers even if they're far away from visible stars. For smaller black holes, including micro-black holes, detection is more challenging. Some theoretical physicists propose that unusual gravitational or magnetic disturbances on Earth could hint at a micro-black hole's presence. Instruments like accelerometers and gravimeters, designed to measure small changes in gravitational pull or movement, could potentially help detect tiny distortions in spacetime caused by a nearby micro-black hole. Black hole size and potential Earth impact. To put black holes in perspective, consider their immense range in size. A stellar black hole, which forms when a massive star collapses, could be anywhere from 10 to 24 kilometers, 6 to 15 miles, in diameter. Meanwhile, a supermassive black hole, like the one at the center of our galaxy, could span millions of kilometers. Micro-black holes, however, might be minuscule, even as small as a single atom in diameter, but with mass comparable to a large mountain. If such a micro-black hole were to exist on Earth, it wouldn't cause immediate catastrophic effects. A black hole's influence depends largely on its size and proximity to other objects. For instance, if Earth were hypothetically orbiting a stellar black hole, the planet would be pulled in and disintegrated. But with a micro-black hole, the gravitational pull would be far weaker, possibly causing subtle effects without catastrophic impact, unless it were to grow over time by absorbing matter, which would then amplify its gravitational force. Understanding the fundamentals of black holes sets the stage for exploring how such an object could theoretically exist on Earth. The concept may seem far-fetched, but modern physics and quantum mechanics have raised possibilities that weren't conceivable even a few decades ago. Could there really be a black hole in our midst, subtly influencing the environment and bending spacetime right under our feet? How could a black hole exist on Earth? The idea of a black hole on Earth sounds like something out of science fiction, but certain theories within modern physics make it a fascinating possibility. For a black hole to exist on Earth, it would likely be a micro-black hole, one formed under unique conditions, potentially during the early moments of the universe. This section will explore how a black hole could theoretically exist on our planet, what factors would allow it to persist, and what types of effects it might have on our environment. Theoretical origins. Primordial black holes and the early universe. Primordial black holes are a concept that originated with physicists considering what might have happened during the early universe. Shortly after the Big Bang, the universe was filled with incredibly high-energy particles and densely packed matter, a state vastly different from anything we observe today. Under these conditions, it's thought that tiny black holes could have formed from the collapse of small regions of high-density matter. Unlike typical black holes formed from stars, these primordial black holes would be small enough to exist on planetary scales but still retain the unique gravitational properties of larger black holes. Primordial black holes could theoretically exist anywhere in the universe, including on Earth. If one of these black holes were caught by Earth's gravitational field billions of years ago, it might have settled in the planet's core or mantle, undetected due to its small size. Since primordial black holes are smaller and less massive than stellar black holes, they wouldn't have the devastating pull of larger black holes, potentially allowing them to coexist with Earth without immediate destruction. CERN and micro-black hole research. The idea of micro-black holes existing on Earth has gained traction with advancements in high-energy particle physics, particularly through experiments conducted at facilities like CERN, the European Organization for Nuclear Research. At CERN, scientists operate the Large Hadron Collider, LHC, the world's most powerful particle accelerator. Here, they collide particles at near light speeds, generating energy levels that, while minuscule compared to natural cosmic events, are incredibly intense for Earth-based experiments. One of the theoretical outcomes of particle collisions at such high energy is the creation of micro-black holes. While none have been detected to date, scientists have hypothesized that creating a micro-black hole could be possible if the conditions are right. These black holes would likely be fleeting, evaporating almost instantly due to a phenomenon known as Hawking radiation. Hawking radiation, theorized by physicist Stephen Hawking, suggests that black holes lose energy over time, eventually evaporating and disappearing. If a micro-black hole were to form and exist on Earth, it would likely be short-lived. However, in an extreme case where a micro-black hole stabilized and avoided evaporation, it could theoretically remain, possibly moving undetected through Earth's layers due to its weak gravitational effects at such a small scale. Signs of a micro-black hole on Earth. If a micro-black hole exists on Earth, how could we detect it? Unlike larger black holes in space that pull in surrounding stars and light, a micro-black hole on Earth wouldn't have a massive gravitational influence. However, it could still leave subtle clues in the form of gravitational or magnetic anomalies. Scientists have speculated that if a black hole were present, it might create tiny distortions in gravity that sensitive instruments, such as gravimeters, could detect. These instruments measure changes in gravitational force, and while a micro-black hole's pull would be small, repeated measurements in specific areas could reveal unexplained gravitational hotspots. In addition to gravitational effects, a black hole could influence magnetic fields. Earth generates a magnetic field through its iron core, and the black hole's gravitational pull, though weak, might affect the behavior of magnetic particles within Earth's crust. This disturbance could theoretically lead to unexplained fluctuations in the planet's magnetic field, which scientists could detect and measure. Impact on Earth's core and geological activity. One of the most intriguing possibilities is the idea that a micro-black hole could be influencing Earth's core. Earth's core is composed mainly of iron and nickel and generates intense heat and pressure. The inner core's heat drives convection currents in the outer core, which is responsible for Earth's magnetic field. If a micro-black hole was situated in the core, it could contribute to these currents, potentially influencing Earth's magnetic field in ways we don't yet understand. Another potential sign of a black hole's presence in Earth's core could be seen in geological phenomena like earthquakes, volcanic eruptions, and tectonic shifts. While these processes are typically driven by Earth's internal heat and pressure, a stable micro-black hole in the core could theoretically add a gravitational force that alters tectonic movements subtly. This influence might be especially noticeable in areas with frequent geological activity, where a small additional force could amplify natural tectonic stresses, potentially leading to more frequent or intense activity. Gravitational waves. Detecting tiny disturbances. Gravitational waves, or ripples in spacetime, are another way scientists could potentially detect a micro-black hole on Earth. When massive objects interact, they produce gravitational waves that travel through the fabric of space and time. Although gravitational waves are typically associated with cosmic events like black hole collisions, smaller disturbances in spacetime can also create minor waves, detectable by highly sensitive instruments. The LIGO and Virgo observatories, designed to detect gravitational waves, have recorded waves produced by black hole mergers millions of light-years away. If a micro-black hole on Earth interacted with dense materials in the planet's core, it might create small gravitational disturbances. While the waves from such a small object would be faint, advances in gravitational wave technology could eventually make it possible to detect even these minuscule signals. Detecting gravitational waves on Earth that cannot be explained by cosmic events or natural geological activity could hint at the presence of a micro-black hole. Limitations and challenges in detecting micro-black holes. Despite the intriguing theories and technologies, detecting a micro-black hole on Earth would be a monumental challenge. For one, the gravitational effects of a micro-black hole are weak, and Earth's natural geological processes create a background of noise that would make detection difficult. Instruments sensitive enough to pick up a micro-black hole's influence would need to isolate signals that might easily be mistaken for natural phenomena. Moreover, scientists would need to determine the specific regions or depths at which to focus their measurements. Earth's surface is vast, and without an idea of where a micro-black hole might reside, the task becomes even more daunting. It's possible that gravitational or magnetic anomalies observed in certain locations could merely be the result of geological formations, mineral deposits, or other natural variables, rather than a micro-black hole. Could human activity create black holes on Earth? Interestingly, some have speculated that human activity could inadvertently create conditions for a micro-black hole to form. High-energy particle collisions at facilities like CERN have sparked discussions about the potential for man-made micro-black holes. While physicists are confident that any black hole created in a laboratory would evaporate almost instantly, some still worry about unknown factors that might stabilize a micro-black hole under certain conditions. To date, no black holes have been created on Earth through particle collisions, and safety studies affirm that even if a micro-black hole were produced, it would pose no threat to the planet. However, the ongoing study of high-energy particle collisions could reveal more about the nature of micro-black holes, helping scientists better understand the conditions required for their existence. This research could be crucial for future studies, as understanding how micro-black holes might behave is essential for both scientific curiosity and practical safety. Exploring the theoretical presence of a micro-black hole on Earth opens a window into the fascinating interactions between physics, geology, and astrophysics. If such a phenomenon exists, it would fundamentally change our understanding of both black holes and Earth's internal processes, bridging the gap between cosmic phenomena and terrestrial science. Real-life case studies, mysterious phenomena linked to black holes. The concept of a black hole on Earth might sound speculative, but when we examine some of the most mysterious and unexplained phenomena around the globe, the theory gains an intriguing layer of plausibility. Certain strange occurrences, from odd gravitational anomalies to unexplained disappearances, have raised questions that science struggles to answer fully. Could these be the subtle signs of a micro-black hole's influence? This section explores real-life cases that some believe could be linked to an Earth-bound black hole. Case Study 1. The Bermuda Triangle, a black hole in disguise. Perhaps the most famous mysterious region on Earth, the Bermuda Triangle, has baffled researchers and fascinated the public for decades. This area, spanning roughly 500,000 square miles between Miami, Bermuda, and Puerto Rico, has been the site of numerous ship and aircraft disappearances. Reports of navigational malfunctions, sudden storms, and vanished vessels have contributed to the Bermuda Triangle's reputation as a dangerous and perplexing zone. One theory proposes that a micro-black hole could be responsible for these incidents. The idea is that a black hole's intense gravitational pull could distort space and time, creating a phenomenon known as gravitational lensing. If a black hole, however small, existed in this region, it might cause unusual fluctuations in gravity, potentially impacting the stability of ships and planes. In such a scenario, a plane or ship passing through the gravitational influence of the black hole could be pulled off course or even torn apart. Additionally, black holes distort electromagnetic fields, which could explain the navigational malfunctions often reported in the Bermuda Triangle. However, skeptics argue that these disappearances can be attributed to natural maritime and meteorological hazards, emphasizing that no concrete evidence links the Bermuda Triangle to a black hole. Case Study 2. Gravity anomalies across the Earth. Scientists have discovered several areas on Earth where gravity behaves in unexpected ways. One well-known example is Hudson Bay in Canada, where gravity is slightly weaker than in surrounding regions. This phenomenon puzzled scientists for years, as gravity is generally consistent at similar altitudes worldwide. Further research revealed that this anomaly might be due to the presence of a massive ice sheet that once covered the region, deforming Earth's crust. However, the persistence of this gravitational dip, even after the ice melted, has led to continued speculation. Some have proposed that a micro-black hole could be at play in regions like Hudson Bay. The gravitational pull of a black hole, though small in a micro-black hole's case, could create localized dips or fluctuations in gravity. While the geological explanation currently holds as the dominant theory, the mystery of gravity anomalies raises questions about other possible contributing factors, including the presence of micro-black holes. Another notable location with strange gravitational effects is the gravity hill phenomenon, seen in various locations around the world, where cars seem to roll uphill, defying gravity. While most gravity hills have been explained as optical illusions, certain regions exhibit persistent gravitational anomalies that are harder to explain, sparking theories of a hidden gravitational source, possibly a black hole. Case Study 3, the vial vortices theory. In the 1970s, researcher Ivan T. Sanderson introduced the concept of vial vortices, which are 12 locations around the world where bizarre occurrences and magnetic anomalies are common. The Bermuda Triangle is perhaps the most famous of these vortices, but other regions include the Devil's Sea near Japan, Easter Island, and the Algerian megaliths in Africa. Sanderson suggested that these vortices align along geometric patterns on Earth, creating areas of high electromagnetic disturbances and unexplained phenomena. Some proponents of the Earth-bound black hole theory suggest that these vortices could be affected by micro-black holes, with each vortex potentially representing a gravitational distortion caused by the presence of a black hole. For example, the Devil's Sea has been linked to mysterious disappearances of fishing boats and the loss of Japanese military vessels in the 1950s. In both the Bermuda Triangle and the Devil's Sea, ships and planes have experienced unexplained navigation issues, similar to effects that might occur in a region influenced by a micro-black hole. While mainstream science attributes these occurrences to natural phenomena like magnetic anomalies or ocean currents, the pattern and similarity of events across the vial vortices keep this theory alive among those fascinated by Earth's mysteries. Case Study 4, Unexplained magnetic disturbances and disruptions across the planet. Certain regions exhibit unusual magnetic characteristics, like intermittent magnetic pulses or shifts. These disturbances are usually linked to variations in Earth's magnetic field, yet some magnetic anomalies remain unexplained. For instance, scientists have observed that areas like the South Atlantic anomaly, a region where Earth's magnetic field is weaker, exhibit strange disruptions that affect satellite operations, spaceflights, and even the behavior of migratory animals. A micro-black hole could theoretically cause slight disturbances in Earth's magnetic field, leading to anomalies like the South Atlantic anomaly. A black hole generates intense gravitational forces that could impact the iron-rich core that generates Earth's magnetic field. This influence might cause unpredictable magnetic pulses, which could create hazardous conditions for satellites or other technology within affected zones. However, the scientific consensus still holds that these disturbances are due to the natural dynamics of Earth's molten core rather than any celestial influence. Case Study 5, Unusual geological events and earthquakes with numbered tectonic source. Another mysterious phenomenon that has puzzled scientists is the occurrence of seismic activity that lacks an identifiable tectonic source. Normally, earthquakes result from tectonic plate movement along faults, but in rare cases, seismic waves have been detected with no apparent fault or plate movement. These so-called mystery quakes have been recorded in several locations, including places with low tectonic activity, sparking debates about their cause. Some speculate that these could be microquakes triggered by the gravitational effects of a micro-black hole interacting with dense materials in the Earth's crust or core. While this theory is far from mainstream, it offers an alternative explanation for these unaccounted-for tremors. If a micro-black hole were indeed present, its gravitational pull might create minute vibrations within Earth's crust, which could be detected as seismic activity. However, the scientific community typically attributes these quakes to less understood geological factors, such as volcanic activity or underground gas movement. Scientific skepticism and alternative explanations. While each of these cases presents intriguing evidence, scientists remain skeptical of attributing them to a micro-black hole. Many scientists argue that these phenomena can be explained by geological, magnetic, or atmospheric factors without invoking the presence of a black hole. For instance, the unusual gravitational readings in places like Hudson Bay are generally understood to be remnants of Ice Age-induced crustal depression, rather than signs of a black hole. Likewise, navigational errors in the Bermuda Triangle are often attributed to high-frequency weather changes, ocean currents, or even human error. Similarly, magnetic anomalies in the South Atlantic and elsewhere can often be traced to complex interactions within Earth's magnetic field, which fluctuates naturally and is influenced by factors like the core's movement and solar winds. These scientific explanations do not negate the mysterious nature of these phenomena but suggest that invoking a black hole on Earth might not be necessary to account for the observed events. However, these conventional explanations have not quelled public curiosity or the desire to explore alternative theories. The concept of a black hole on Earth remains appealing to those who seek to push the boundaries of science and explore the unknown. The role of technology in solving the mystery. With advancements in technology, the potential to understand these mysteries grows. Instruments like accelerometers, gravimeters, and satellite-based measurements are improving in precision, making it possible to detect smaller and more subtle anomalies. Gravitational wave observatories could also play a role in investigating potential Earth-bound black holes, as their sensitivity increases to detect minute ripples in space-time. Additionally, machine learning and AI are enhancing scientists' abilities to analyze vast datasets collected from these phenomena. By comparing patterns in gravitational, magnetic, and seismic data from areas associated with the Vial vortices or the Bermuda Triangle, researchers might find new insights that either strengthen or debunk the Earth-bound black hole theory. These real-life case studies highlight how the Earth-bound black hole theory can offer a new lens through which to view long-standing mysteries. Whether or not there is a black hole on Earth, the theory encourages fresh exploration of these phenomena, challenging conventional explanations and inspiring a new generation of scientific inquiry. Controversial insights. Scientists who believe in terrestrial black holes. The possibility of a black hole existing on Earth is a fringe theory, yet it has attracted the attention of some scientists who are willing to entertain the idea. While most researchers agree that an Earth-bound black hole is unlikely, there is a small but growing body of thought-provoking ideas and theories from physicists who challenge conventional views. These scientists propose alternative models that allow for the existence of black holes in unusual places, even within our planet. Physicist Paul Davies and micro-black holes. One of the prominent voices in this field is theoretical physicist Paul Davies. Known for his work on cosmology and quantum mechanics, Davies has suggested that micro-black holes might be scattered throughout the universe, including potentially on Earth. He bases this idea on the theory that the early universe's conditions were so extreme that miniature black holes could have formed alongside regular matter. While most of these primordial black holes would have dissipated over time due to Hawking radiation, Davies theorizes that some could be stable, trapped in planetary systems or even within planets themselves. According to Davies, if a micro-black hole were trapped within Earth, it might be small enough to avoid catastrophic consequences while still exerting a minor gravitational influence. Davies hypothesizes that the behavior of this black hole would be subtle, likely limited to gravitational or magnetic anomalies that would be challenging to detect with current technology. While this concept remains speculative, it has fueled interest in the possibility of micro-black holes lingering in hidden regions across the universe. Stephen Hawking's theory of black hole evaporation. Stephen Hawking's groundbreaking research on black holes introduced the concept of Hawking radiation, the process by which black holes emit radiation and lose mass over time. Hawking radiation theoretically leads to the eventual evaporation of black holes, especially those of smaller sizes, like micro-black holes. Hawking speculated that if micro-black holes do exist, they would evaporate quickly, leaving no lasting impact on their surroundings. However, some scientists believe that if a micro-black hole was somehow stable and shielded from evaporation, perhaps due to particular environmental conditions, it could persist longer than previously thought. This Hawking stable, micro-black hole could theoretically exist within a planet like Earth. While the scientific community largely views Hawking's work as confirmation that black holes on Earth are improbable due to evaporation, this counter-theory remains a topic of debate and inspires further investigation into black hole behavior. Nobel laureate Roger Penrose and quantum gravity. Roger Penrose, renowned for his research on general relativity and cosmology, has also made contributions to the theoretical understanding of black holes. Penrose's work suggests that black holes could form in different ways under extreme conditions, such as those present in the early universe. Although Penrose himself hasn't proposed that black holes exist on Earth, his theories on quantum gravity open the door to unconventional ideas about black hole formation and behavior. One aspect of Penrose's work focuses on the quantum nature of space-time. According to some interpretations, quantum fluctuations could theoretically create tiny black holes, which might not behave in the same way as conventional black holes formed from stellar collapse. If these quantum-created black holes exist, they could interact with matter differently, allowing them to remain hidden or exhibit unique properties that distinguish them from typical black holes. This interpretation challenges traditional physics and leaves open the possibility of unusual black hole-like phenomena on Earth. Controversial ideas from modern physicists. The fuzzball theory. In recent years, a group of physicists led by Samir Mathur proposed an alternative model of black holes known as the fuzzball theory. According to fuzzball theory, black holes are not singular points but rather clusters of quantum strings or fuzzballs with complex internal structures. This theory challenges the classic notion of black holes as points of infinite density, suggesting that black holes might instead be composed of tangled strings and quantum information. While fuzzball theory has yet to gain widespread acceptance, it presents an interesting possibility for the existence of black hole-like objects in unexpected places. If fuzzballs could form under certain conditions within Earth, they would likely appear as localized regions of high gravity or electromagnetic activity. Such a phenomenon could explain some of the gravitational and magnetic anomalies observed in specific areas on Earth. Though the fuzzball theory remains speculative, it expands our understanding of what a black hole might be and where it could exist. Physicist Nikodem Poplawski and black holes as portals to other universes. Another intriguing perspective comes from physicist Nikodem Poplawski, who has suggested that black holes could function as wormholes or gateways to other universes. Poplawski's research explores the idea that each black hole might contain a universe within it, a concept known as the black hole cosmology theory. While his research primarily focuses on cosmic-scale black holes, Poplawski's work raises questions about whether micro-black holes could have similar properties on a smaller scale. If a micro-black hole on Earth were capable of creating a tiny wormhole, it could theoretically cause unusual gravitational and magnetic effects, influencing surrounding matter in ways that would be difficult to detect with current instruments. While there's no empirical evidence supporting the existence of black hole-generated wormholes on Earth, Poplawski's theory has broadened the scope of black hole research, leading scientists to consider other possibilities for black holes and their interactions with matter. Critics and the mainstream scientific response. Despite the curiosity these ideas generate, the mainstream scientific community remains cautious and often skeptical. Critics argue that the physics supporting black holes on Earth is speculative at best and lacks empirical evidence. The most prominent objection is rooted in the immense gravitational force that black holes exert. Even a micro-black hole would require an extraordinary set of conditions to exist on Earth without causing significant, observable effects. For instance, any black hole with enough mass to persist over time would likely have a gravitational influence that would disrupt geological structures and cause noticeable disturbances. Additionally, skeptics emphasize that the current understanding of black holes aligns with the idea that they are cosmic phenomena rather than planetary ones. The scientific consensus holds that black holes are unlikely to exist on Earth, as the planet does not provide the high energy conditions needed to sustain a black hole, especially with the presence of Hawking radiation leading to black hole evaporation. The value of unconventional theories in scientific progress. Though the scientific community may dismiss many Earth-bound black hole theories as fringe ideas, exploring these possibilities plays an essential role in advancing our understanding of black holes and quantum mechanics. Theoretical physicists like Davies, Hawking, and Penrose have consistently pushed the boundaries of established science, challenging assumptions and inspiring new experiments. By questioning whether black holes could exist on Earth, scientists force themselves to investigate the limits of what we know and explore potential connections between quantum mechanics, gravity, and black hole physics. In many ways, these unconventional theories encourage researchers to pursue new directions in black hole research, even if they ultimately prove the Earth-bound black hole theory to be unlikely. They also lead to technological advancements, as scientists develop increasingly sensitive instruments to detect gravitational waves, measure magnetic fields, and observe minute cosmic events. Such advancements are crucial, not only for black hole research but for all fields of physics. While controversial, the theories proposed by scientists open a door to alternative perspectives, encouraging a deeper exploration of our universe's mysteries. The idea of a black hole on Earth may remain unlikely, but these scientific insights offer an exciting glimpse into the possibilities of our planet's interactions with cosmic phenomena. Whether or not we ever discover a black hole on Earth, the quest to understand black holes continues to reshape the frontiers of science, sparking curiosity and expanding human knowledge. What would happen if there were a black hole on Earth? To grasp the potential implications of a black hole existing on Earth, we need to explore the hypothetical scenarios that might unfold if such an extraordinary phenomenon were real. The presence of a black hole on Earth would introduce complex gravitational and environmental challenges, impacting not only physical structures but also life on the planet. Let's walk through various scenarios that illustrate the possible consequences of a black hole on Earth, from micro-black holes to larger masses, and how these would affect Earth's environment, stability, and inhabitants. Scenario 1. A micro-black hole's subtle influence. In the case of a micro-black hole on Earth, the effects would likely be minimal due to its small gravitational pull. Micro-black holes are theorized to have significantly less mass than stellar black holes and would thus generate a weaker gravitational field. In this scenario, the micro-black hole might exist in a stable orbit within Earth's interior, interacting only slightly with its surroundings. The gravitational influence of such a black hole could cause minor anomalies in Earth's magnetic field, creating localized fluctuations. Sensitive instruments might detect gravitational waves or minor gravitational anomalies in areas close to the micro-black hole. However, given the limited pull of a micro-black hole, this scenario wouldn't pose any immediate risk to human life or planetary stability. The most likely outcome would be an increase in scientific research to better understand the source of these anomalies and the development of technology to monitor its effects. Scenario 2. Geological and environmental changes. If a micro-black hole were positioned within Earth's core, it could subtly influence geological processes over time. The gravitational pull of the black hole could interact with Earth's molten iron core, potentially altering the dynamics that drive the magnetic field. Earth's magnetic field is essential for shielding the planet from harmful solar and cosmic radiation, and any changes to it could have far-reaching consequences. For example, disturbances in the magnetic field might weaken the natural protection it provides, leading to higher levels of radiation reaching Earth's surface. This increased exposure could affect electronic systems, disrupt satellite communications, and even impact the health of humans and animals sensitive to radiation. Additionally, changes to the magnetic field might disrupt the behavior of migratory animals that rely on magnetic navigation. On a geological level, a micro-black hole could influence tectonic activity. While it wouldn't directly cause earthquakes, its presence could add a small gravitational force, amplifying stress along fault lines. Over long periods, this influence could contribute to more frequent or intense seismic activity, particularly in tectonically active regions. Similarly, volcanic activity might increase if the black hole were to exert gravitational force near magma chambers, potentially contributing to more eruptions or altering the volcanic cycles. Scenario 3. A stable black hole with a growing mass. In a more extreme scenario, imagine a micro-black hole that somehow begins to grow by absorbing nearby matter, such as rock or metals in Earth's core. While this scenario is hypothetical, it helps illustrate the potential risks of a black hole increasing in size and mass over time. As the black hole consumes more matter, its gravitational field would intensify, exerting greater influence on its surroundings. A growing black hole in Earth's core could gradually destabilize the planet's internal structure. Over time, it might affect the flow of molten rock within the mantle, disrupting convection currents that drive tectonic movements. This disruption could lead to intensified earthquakes, shifting tectonic plates, and changes in volcanic activity, particularly near areas where the black hole's influence is strongest. This effect might eventually cause severe geological instability, with unpredictable consequences for regions along fault lines. As the black hole absorbs more material, the gravitational effects could extend beyond the core, impacting Earth's crust. In this scenario, we might observe sinkholes, land subsidence, and shifts in terrain near areas where the black hole's gravitational pull is strongest. These shifts would pose significant risks to infrastructure, potentially damaging buildings, roads, and other structures. However, this scenario remains largely theoretical, as micro-black holes are not believed to absorb matter rapidly enough to reach such a size. Scenario 4, extreme effects of a larger black hole. For the sake of understanding, let's consider an even more extreme, though unrealistic, scenario, a stellar mass black hole on Earth. This situation would be catastrophic, as a stellar black hole's gravitational force would be strong enough to disrupt the entire planet. Unlike a micro black hole, which might coexist with Earth, a stellar black hole would instantly attract and compress nearby matter, including Earth's core and crust. In this scenario, Earth would not survive intact. The intense gravitational field of a stellar black hole would rip the planet apart, tearing through rock, metal, and all matter in its vicinity. Within seconds or minutes, Earth would collapse toward the black hole, resulting in a dramatic end for the planet. Fortunately, such a scenario is impossible under natural conditions, as stellar black holes are typically formed in the aftermath of a massive star's collapse, far from any planetary system. Impact on life and technology. Even in the more plausible scenario of a micro black hole with a limited gravitational effect, life on Earth could still experience indirect impacts. As mentioned, disturbances to Earth's magnetic field could increase radiation exposure, particularly in areas where the magnetic shield is weakened. This could lead to a higher incidence of radiation-related health issues, especially in regions at higher altitudes or near the poles, where Earth's magnetic field is naturally weaker. Additionally, increased radiation could disrupt telecommunications and navigation systems that rely on satellites. Solar storms, which are already a threat to satellite systems, would become more damaging without the full protection of Earth's magnetic field. The increased vulnerability of satellites would disrupt GPS navigation, internet communications, and other technology-dependent systems, creating challenges in transportation, communication, and global commerce. In agriculture, higher levels of radiation could impact crop yields, as radiation exposure affects plant growth and food quality. Livestock and wildlife, especially species that rely on magnetic fields for migration, would also be affected, potentially altering ecosystems. These environmental impacts could lead to shifts in food production, ecological balance, and economic stability, depending on the severity of the magnetic disturbances. What scientists predict about an Earth-bound black hole? While the idea of a black hole on Earth is largely theoretical, scientists have explored some predictions about its behavior if such a phenomenon were ever to occur. Many physicists believe that a micro-black hole would remain harmless, either evaporating quickly due to Hawking radiation or exerting such a weak gravitational pull that it would have no significant impact on Earth. If a stable micro-black hole did exist, its influence would be so minor that it would remain undetectable under current measurement capabilities. Research into black hole behavior on Earth also offers insights into developing detection methods. For instance, if gravitational waves could reveal the location of a micro-black hole, scientists might be able to study its impact on Earth's interior over time. As technology advances, our ability to detect minuscule gravitational or magnetic anomalies may eventually confirm or rule out the presence of black holes on Earth, offering valuable insights into planetary physics and black hole dynamics. An unlikely but fascinating hypothesis: the concept of a black hole on Earth sparks the imagination, blending scientific principles with hypothetical scenarios that stretch the limits of what we know. While scientists agree that the likelihood of a black hole existing on Earth is exceedingly low, exploring this idea reveals valuable lessons about our planet's stability and resilience. It also highlights the importance of understanding gravitational and magnetic forces that shape our world, inspiring future research that may uncover new information about the fundamental forces of the universe. In the end, a black hole on Earth may remain in the realm of fiction or theoretical discussion, but it underscores the broader quest for knowledge about our planet and the cosmos. The thought of coexisting with such a force reminds us of the mysteries that lie beneath our feet, within our atmosphere, and beyond our reach in the vastness of space. Dismissing the myths, why this theory may not hold. While the idea of a black hole on Earth is intriguing, the scientific consensus strongly argues against it. This section will break down the main scientific reasons why an Earth-bound black hole is considered highly improbable. From the basic principles of black hole formation to the evidence that counters popular myths, we'll explore why the majority of scientists view the concept as more myth than reality. Myth 1. The conditions required to form a black hole. One of the primary reasons why black holes are unlikely to exist on Earth has to do with the extreme conditions required for their formation. Black holes typically form when massive stars collapse under their own gravity at the end of their life cycle. For this to happen, a star must reach a critical mass threshold that causes its core to collapse, creating the gravitational singularity and event horizon that characterize black holes. The Earth, by contrast, is not massive enough to initiate such a collapse. Its mass and density are far lower than that of even the smallest stars capable of becoming black holes. The gravitational forces on Earth simply aren't strong enough to compress matter to the density required to form a singularity. Without the presence of a dying, massive star, Earth lacks the essential elements needed to give birth to a black hole, even a micro one. Myth 2. Micro black holes and Hawking radiation. While there is theoretical support for the existence of micro black holes, small black holes that might have formed in the early universe, Hawking radiation suggests that these black holes wouldn't survive long. Stephen Hawking's groundbreaking research on black holes introduced the concept of Hawking radiation, which implies that black holes lose mass over time by emitting radiation. The smaller a black hole, the faster it would lose mass, eventually evaporating entirely. For micro black holes, this process would happen almost instantaneously. Any micro black hole that might form on Earth would emit Hawking radiation at such a rapid rate that it would effectively evaporate before it could influence its surroundings. This radiation theory serves as one of the key reasons scientists dismiss the notion of micro black holes lingering on Earth. It suggests that even if a micro black hole were created in high-energy environments like particle accelerators, it would vanish before posing any risk. Myth 3. Particle colliders and the safety debate. With advancements in particle physics, concerns about black hole formation on Earth have often centered around high-energy particle colliders, like the Large Hadron Collider, LHC, at CERN. Some theories suggest that particle collisions at these energy levels could theoretically create micro black holes. However, exhaustive safety analyses conducted by CERN and other research organizations have consistently found that these concerns are unfounded. The reason lies in the nature of the collisions and the energies involved. While the energy levels achieved in particle colliders are impressive, they are still far lower than the cosmic ray collisions that naturally occur in Earth's atmosphere daily. These cosmic rays involve much higher energy particles striking Earth's atmosphere, yet no black holes have been detected as a result. Thus, if high-energy collisions were capable of creating black holes, we would likely have observed them by now in nature. The fact that these cosmic rays have never led to detectable black holes reinforces the scientific stance that particle colliders pose no threat of forming black holes on Earth. Myth 4. Gravitational impact and detectability. If a black hole, even a micro one, were to exist on Earth, it would exert a noticeable gravitational influence on its surroundings. Black holes are defined by their intense gravitational fields, which can alter the behavior of nearby objects. The presence of a black hole would likely lead to measurable gravitational distortions or anomalies, which scientists could detect using instruments like gravimeters. While Earth does have regions with minor gravitational anomalies, these are generally understood to be the result of variations in geological density, such as differences in rock types or underground voids. Studies of Earth's gravitational field, conducted by space missions like NASA's GRACE satellites, have found no evidence of any unexplained gravitational effects that would suggest the presence of a black hole. If a black hole were exerting a gravitational pull, it would likely distort Earth's surface, creating anomalies far stronger than those caused by natural geological factors. Myth 5. Lack of observable radiation or energy signatures. Another hallmark of black holes is their energy signature. Black holes, particularly those with accretion disks, emit X-rays and other forms of radiation as they pull in surrounding matter. Even a micro black hole would likely interact with its surroundings, generating some form of detectable energy. Yet scientists have found no unexplained radiation or energy sources on Earth that could be attributed to a black hole. For instance, studies using gamma-ray detectors and X-ray observatories have failed to identify any abnormal radiation patterns that would suggest a micro black hole's presence. The absence of these energy signatures reinforces the view that black holes are unlikely to exist on Earth, as their presence would likely reveal itself through some form of detectable radiation. Myth 6. Theories of primordial black holes and why they don't apply. Primordial black holes are thought to have formed during the extreme conditions of the early universe. Some theories suggest that these black holes might still exist today, possibly as micro black holes scattered throughout space. However, scientists largely agree that if primordial black holes did exist, they would be extremely rare and distributed across vast regions of space. The likelihood of one being captured by Earth's gravitational field is exceedingly low, given the vast distances and sparse distribution of these black holes. Even if a primordial black hole did enter Earth's orbit, it would likely be ejected due to gravitational interactions with the Sun, Moon, or other celestial bodies. Earth's gravitational pull isn't strong enough to retain a free-floating primordial black hole, making it improbable that one would remain on the planet for any extended period. Myth 7. Magnetic and gravitational anomalies explained by conventional science. Certain phenomena, like the Bermuda Triangle's mysterious incidents or regions with magnetic disturbances, have fueled speculation about Earth-bound black holes. However, these occurrences have more plausible explanations rooted in conventional science. For example, areas like the Bermuda Triangle are known for sudden weather changes, strong ocean currents, and other natural factors that can contribute to disappearances or navigation issues. Similarly, magnetic anomalies are often caused by variations in the composition of Earth's crust, rather than the presence of a black hole. Gravitational anomalies, such as those observed in areas like Hudson Bay, are typically explained by variations in geological density, tectonic activity, or the remnants of past glacial activity. These explanations, supported by geological and geophysical research, provide clear evidence that these anomalies are natural and do not require a black hole to explain their presence. Myth 8. The role of scientific consensus and peer review. Science relies heavily on peer-reviewed research and consensus building within the scientific community. The idea of a black hole on Earth has been explored by theoretical physicists, but it has not gained support within the mainstream scientific community. Rigorous scrutiny and repeated testing are necessary to validate scientific theories, and the black hole on Earth hypothesis lacks the empirical support to withstand this level of examination. The mainstream scientific consensus, based on decades of research and observation, concludes that black holes are cosmic entities formed under conditions that Earth cannot replicate. The notion of an Earth-bound black hole remains speculative and unsupported by credible evidence. Without observable data or experimental results to back this theory, it remains outside the bounds of accepted scientific understanding. Separating fact from fiction. The idea of a black hole on Earth is a captivating narrative, blending elements of astrophysics with human curiosity about unexplained phenomena. While it's an entertaining concept, the scientific community overwhelmingly rejects it based on the evidence available. The principles of black hole formation, Hawking radiation, and gravitational physics all suggest that black holes are highly unlikely to exist within Earth. Moreover, the lack of observable energy signatures, gravitational effects, or radiation further diminishes the plausibility of this theory. From a scientific standpoint, black holes remain the enigmatic giants of space, bound to regions where the laws of physics allow them to form. However, the mystery and allure of a black hole on Earth continue to inspire new scientific exploration and technological advancements, reminding us of the endless wonders the universe has yet to reveal. Implications for science and future research. Even though the idea of a black hole on Earth may seem improbable, exploring this possibility has important implications for science, technology, and our understanding of the universe. The scientific pursuit of understanding black holes and the hypothetical exploration of an Earth-bound black hole inspire advancements in fields like quantum mechanics, particle physics, and gravitational wave research. This section examines how the study of black holes on Earth can push scientific boundaries, the future of black hole research, and what implications this has for humanity. Advancing quantum mechanics and general relativity. Black holes are unique cosmic phenomena that test the limits of physics, especially the relationship between quantum mechanics and general relativity. Quantum mechanics, which deals with the smallest particles in the universe, and general relativity, which addresses massive objects and gravity, are two fundamental theories in physics that don't entirely align when applied to black holes. Black holes represent extreme conditions where both theories converge, and they expose the limitations and contradictions in our understanding of the universe. The hypothetical study of black holes on Earth drives scientists to bridge the gap between these theories. For example, understanding micro-black holes on Earth would require physicists to develop models that explain both gravitational and quantum effects. Research into quantum gravity, a field that seeks to unify quantum mechanics and general relativity, may ultimately provide insights that answer fundamental questions about black holes and the fabric of space-time. If such advancements are achieved, they could redefine physics itself, influencing everything from fundamental science to advanced technologies. New frontiers in gravitational wave research. In recent years, gravitational wave observatories like LIGO, Laser Interferometer Gravitational Wave Observatory, and Virgo have opened a new window into understanding black holes. These observatories detect gravitational waves, ripples in space-time created by massive cosmic events, such as black hole mergers. Gravitational wave detection has provided conclusive evidence of black hole collisions in deep space, confirming theories about their existence and behavior. If a micro-black hole or any black hole-like object were to exist on Earth, its gravitational effects might create detectable ripples, even if small. Studying gravitational waves within Earth could offer new opportunities for understanding local gravitational phenomena. Scientists could explore how these waves interact with Earth's mass and magnetic fields, potentially revealing insights about Earth's internal structure and the behavior of gravity on a smaller scale. While current gravitational wave detectors are focused on distant cosmic events, future instruments could be refined to observe minute local gravitational waves, offering a fresh perspective on Earth's gravitational environment. Technology and instrumentation development exploring the possibility of black holes on Earth, even as a hypothetical scenario, encourages the advancement of technology for detecting minute gravitational and magnetic anomalies. Instruments like gravimeters, accelerometers, and magnetometers measure tiny changes in gravitational and magnetic fields, and these tools are continually improving in sensitivity. Advancements in these instruments could provide invaluable data for not only black hole research but also for broader scientific applications, such as understanding Earth's geological processes, detecting hidden resources, and monitoring changes in the environment. For example, if scientists were to develop ultra-sensitive instruments capable of detecting faint gravitational anomalies, these tools could be applied in resource exploration, locating underground mineral deposits or oil reserves by detecting gravitational variations. Similarly, magnetometers capable of mapping Earth's magnetic field in detail would aid in understanding the effects of solar activity on our planet, which has implications for technology, communication, and weather patterns. The pursuit of black hole detection on Earth, therefore, indirectly benefits various fields of research and industry. The future of particle physics and high-energy experiments. Particle physics plays a key role in advancing our understanding of black holes, particularly micro-black holes, which could hypothetically be created under extreme conditions. Experiments conducted at particle colliders like CERN's Large Hadron Collider, LHC, continue to explore the limits of matter, energy, and particle interactions. While black hole creation at the LHC is highly unlikely, research in high-energy physics provides insights into the conditions that could hypothetically create micro-black holes. The study of these collisions helps physicists examine the early universe's conditions, where primordial black holes might have formed. By replicating small-scale, high-energy environments, scientists gain a deeper understanding of the particles and forces that govern matter. Moreover, particle collider research could one day provide evidence of exotic particles or phenomena that mimic black hole-like properties, helping scientists understand how black holes interact with matter on a subatomic level. This research could lead to new discoveries about black holes, matter, and the nature of the universe itself. Implications for space exploration and astrophysics. Understanding black holes on Earth could also influence the future of space exploration. Black holes hold potential clues for understanding extreme energy sources, gravitational fields, and space-time manipulation. Hypothetically, if scientists could learn to harness or understand the gravitational properties of micro-black holes, it could open pathways to advanced space propulsion systems or energy solutions, dramatically altering space travel and exploration capabilities. Exploring black holes might also reveal new insights into planetary formation, the life cycle of stars, and the dynamics of galaxies. For example, black holes at the centers of galaxies play a crucial role in shaping those galaxies, influencing star formation and movement. If scientists could replicate even small-scale black hole effects on Earth, they might gain new insights into the role of black holes in cosmic evolution and galactic structures, enhancing our understanding of the universe's origins and its future. Rethinking Earth's geological and magnetic mysteries. The idea of a black hole on Earth, even if theoretical, encourages scientists to revisit unresolved geological and magnetic phenomena. Gravitational anomalies, magnetic field shifts, and unusual seismic activity could potentially be explained by factors related to gravity and electromagnetism on a micro level. While black holes may not be the answer, exploring these questions could lead to other explanations for Earth's gravitational and magnetic behavior. For instance, Further investigation into Earth's gravitational and magnetic anomalies might reveal new patterns in tectonic activity, helping to predict earthquakes or volcanic eruptions with greater accuracy. By understanding the limitations and potential sources of these anomalies, scientists can enhance models of Earth's inner structure and magnetic field dynamics. This could lead to improved natural disaster preparedness, as well as deeper insights into the geological processes shaping our planet. Expanding human curiosity and inspiring future generations. The fascination with black holes, whether they're in distant galaxies or hypothetically on Earth, captures human curiosity about the unknown. The possibility of discovering such a phenomenon close to home inspires young scientists, drives public interest in science, and promotes funding for research and technological advancement. The pursuit of answers to complex questions like these encourages people to think beyond the limits of what we know, fostering a culture of curiosity and exploration. Educational outreach, documentaries, and public discussions about black holes and gravitational phenomena fuel interest in science, particularly in physics and astronomy. The idea of black holes resonates with people of all ages, helping to demystify advanced scientific concepts and make them accessible to a broader audience. As interest grows, so does support for scientific research, creating a positive feedback loop that advances our understanding of the universe and humanity's place within it. The long-term benefits of black hole research. Even if a black hole on Earth remains a theoretical curiosity, the implications of studying it are far-reaching. The exploration of black holes, both near and far, drives progress in technology, fuels scientific discovery, and expands the scope of human knowledge. As scientists continue to study black holes and their extreme properties, they are likely to unlock new principles of physics, unravel cosmic mysteries, and develop technologies that benefit life on Earth. The search for answers about black holes, whether in space or hypothetically on Earth, keeps pushing the boundaries of science, fostering a spirit of inquiry that propels humanity forward. Although black holes may remain in the vastness of space, their influence on our understanding of reality continues to shape science, reminding us that the universe is filled with wonders waiting to be discovered. In our quest to understand the universe, few concepts captivate the imagination quite like black holes. These powerful cosmic entities stretch our understanding of physics and challenge what we know about the nature of reality. The idea of a black hole on Earth might seem improbable, an idea more fitting for science fiction than scientific inquiry. Yet, as we've explored, the question itself opens doors to fascinating realms of scientific theory and discovery. Black holes, from the supermassive giants at the centers of galaxies to the hypothetical micro-black holes, demonstrate the extreme conditions under which matter and gravity interact. While scientists agree that the formation of a black hole on Earth is highly unlikely, exploring this idea pushes the boundaries of what we know about gravitational forces, quantum mechanics, and the behavior of our planet. It encourages us to consider how fundamental forces might interact under different conditions, influencing everything from the magnetic field to seismic activity. We've examined various perspectives, from the possibility of primordial black holes to the speculative theories about black holes creating gravitational anomalies in mysterious regions on Earth. Through real-life case studies, controversial insights from physicists, and analyses of potential impacts, we've delved into the science and myth surrounding the black hole on Earth hypothesis. Though unlikely, the thought experiment fuels advancements in technology, observational methods, and theoretical physics, bringing us closer to answering fundamental questions about the universe. As scientific instruments grow more sensitive and our ability to measure gravitational and magnetic fluctuations improves, humanity edges nearer to detecting phenomena that could once only be theorized. Regardless of whether a black hole exists on Earth, the curiosity driving these explorations is invaluable. Black holes, in all their mystery, compel us to confront the unknown, making them one of the most enduring and inspiring topics in modern science. Ultimately, this journey reminds us of the boundless mysteries waiting to be uncovered, both on Earth and beyond. The hypothetical black hole on Earth may remain an elusive concept, but it underscores humanity's endless quest for knowledge, challenging us to keep asking questions about the forces shaping our world and the universe beyond.